this slide, so everybody knows we're starting. 6033 in the news is not on this slide. I do have news for you though. So we're gonna come back to this news. So let me find where I put the browser window with the news. Okay, so I was gonna tell you some things about the Federal Reserve System today, but I thought it would be more fun, a little bit more fun for today to try to tie lecture with the news. So I'm gonna bring over a browser here for a second. So this is slightly less recently in the news. This is from this past summer. So there was a big outage in July when Cloudflare, this is an outage in Cloudflare. Cloudflare is sort of a company that provides a lot of infrastructure for websites. I think that is the most succinct version I could describe to you. So you can see that they made this blog post that there was an outage, an internet outage. It lasted for about a half an hour. They saw this kind of crazy drop in traffic, and you can actually, I'll put a link to this on Piazza or something if you want to read this blog post. They have some nice visualizations. I thought this was sort of cool. So you can see this period traffic sort of drops for all of these systems and then spikes. So the question to ask here is like, well, what happened, right? Why did this happen? And so the reason this happened is something that we're going to talk about today. So if you continue to read, which we're going to scroll very fast, you can see what happened. All right. So instead of removing the Atlanta routes from the background, a one-line change started leaking all BGP routes into the backbone. So what does that mean? Well, there's this protocol called BGP. That is the topic of today's lecture. BGP involves a lot of human intervention, and sometimes humans do things incorrectly, and it can really kind of destroy routing on the internet for a little bit. So it can send traffic to the wrong place. It can cause drops in traffic, all sorts of things. So we're going to come back to this and talk about why this happens and whether there's anything about that we could change about BGP that would improve this, or whether this is strictly human error, or whatever. We are not ever going to worry about this type of syntax. So this is our 6033 in the news from last summer. So, okay, let me take this away. Now we'll talk about lecture. All right, so we're going to talk about routing with scale, routing with policy. We're going to focus really on one protocol, BGP, which is my favorite protocol. So I will explain why by the end of lecture. All right, so if you remember last time, we were talking about routing last time, right? On Monday, we talked about link state routing. We talked about distance vector routing. They take sort of two different approaches to routing, but these are both routing protocols that certainly allow nodes in the network to determine min cost routes, right? Nothing really wrong with either of those protocols, except that they're not going to scale to the sides of the internet, right? We're not going to be able to use, say, a link state protocol like OSPF, which I have highlighted here on the slide, across all of the end hosts on the internet. And another thing that those protocols don't do is address any sort of policy routing. So you'll remember from when we talked about the history of the internet, there was a point in the internet around, the early 90s when some parties, some players and the internet's infrastructure said, well, we own this set of links and we don't want certain type of traffic to travel across it, right? Namely, you had institutions like the NSF not wanting commercial traffic to run across your links. And link state and distance vector is certainly, as I described them to you, don't really provide for that, right? Perhaps they could be changed, but as is, they don't give you that. All right, so today, we're going to address both of these things, right? Scale and policy. So we are thinking specifically about the internet today. We're not just thinking about any network. And if you notice from the slide, abnormally, I actually haven't highlighted any of these 4 layers, all right? So we'll talk about that later on in this lecture, all right? But let's get started. The first things we're going to talk about are how we deal with scale. All right, there are a couple of things that help us scale to route across the entire internet. So the first thing that you have to know is what the internet looks like. So the internet is divided into sort of different, well, we'll call them modules, different modules, which on the internet we call autonomous systems. All right, so I'm gonna do a little drawing for you. I'll do it in blue. That seems like a nice color. All right, so what is an autonomous system or an AS? So it could be lots of different things. It could be something like a university, all right? So MIT is an AS. All right, so here we have MIT, right? Harvard. Right, we'll get nicer pictures in a minute. This is just freestyling. Could be government labs, right? The NIH. It could be ISPs. In fact, that's a very, very common way to think about an AS. So Comcast is an ISP that some of you might be familiar with. Verizon, I just drew a bunch of them here. AT&T, all right. I've drawn these in no particular place on the slide, but these are all examples of autonomous systems, right? Each of these autonomous systems gets its own unique number. That's how we name them. MIT is autonomous system number 3 on the internet, which means we got into this game very early. And the way you can think about this is that these entities control the stuff within, right, within this AS. So like there's a bunch of different machines at MIT, right, all these little green X's. And MIT has ownership over those MITs, over those machines, it's managing those machines, right? So this is sort of describes the internet in a way by like who owns what, right? And so within an autonomous system, to route within one of these ASs, we use link state routing typically. That is where the protocol that you've seen on the first slide, OSPF, comes in. That means that within MIT, like on campus, pretty much all of those routes would be dictated by a link state routing protocol. So link state routing can scale decently large. Like MIT is not a small network by any means. But to go between ASs, we use a different protocol, right? So the protocol that we're going to use here is BGP. So when we think about scale on the internet, this is part of how we scale. We have a hierarchy of routing, right? There are routing protocols within an AS, and then there is a routing protocol that goes between ASs, right? You can see on this little picture that I've drawn here, we're going to get the other stuff. Oh, spoilers. We'll get the other stuff back, so just ignore that for a second. You can see that these ASs I've drawn with little, they have some gateway routers, we might call those. So that's like routers kind of sitting on the edges of the autonomous systems. They would speak link state on one side and speak BGP on the other side. So these little gateways that help them make that transition. We don't need to worry too much about exactly how those gateways operate. We're going to care more about what is this protocol like overall. All right, so this is part 1 to get scale, and this is huge. You've seen hierarchy to get scale before. You've seen DNS, an enormous hierarchy. You've seen hierarchy in page tables to help them scale. All right, so hierarchy for scale is a thing you are familiar with. Second thing, when we were discussing distance vector and link state, we saw that link state is really robust to failure. And the main reason why it's so robust is because it sends so many copies of all of these advertisements. It floods advertisement. And that overhead is largely what prevents it from scaling, right? And then to contrast, distance vector had much less overhead, but we had some tricky things with failure. We could have a situation where we got into routing loops, right? So packets are just sort of going around and around and around in the network until all of the nodes realized that in fact there was no route to a particular destination. That describes our counting to infinity situations. So typically we use distance vector routing only in small networks where we can make guarantees about the existence or really the non-existence of routing loops. But I sort of hit some things for you. There is a protocol in the middle, right, that is neither link state nor distance vector. It is known as path vector, right? Path vector routing is a very similar style to distance vector. It looks more like distance vector than link state, right? So advertisements are getting sent to neighbors. There's not flooding. But the thing that is different is that the advertisements in path vector, in addition to, they reflect the routing tables, they reflect nodes and costs, they also include path information, right? So I might say, I have a path to Wesley, and it's me, Karen Howie Wesley, something like that. That would be part of my advertisement. And as you start sending those advertisements around, you can infer what your path would be, right? If Karen's sending out advertisements and says, hey, I have a path of cost 6 to Wesley and it's me, Howie Wesley. If I decide to send packets to Wesley via Karen, I just add myself to that path, right? I can build up the paths in that way. Right, so why does this help? This helps because it changes the way that nodes integrate these advertisements. Nodes are going to do the integration in basically the same way you saw on Monday, except they're not going to integrate any route that would cause a routing loop. So if I were to look at an advertisement and I saw that Karen's advertising some path and I'm already part of a path, I'm not going to use that path. That would be a loop. I'd be in the path twice. So because of that, we actually get out of all of those situations that we got into on Monday. The downside, of course, advertisements are bigger, right? They include path information that, like, in terms of bytes, the advertisements consume more bytes on the network. But we still end up in a nice middle ground, right? So it's, yeah, it's more overhead than distance vector, but it's not the overhead that we see with link state. Right, so path vector routing, when we start really talking about BGP, BGP is a path vector routing protocol. All right. Third thing that helps with scale is the way that we deal with addressing. All right, so BGP does provide routes across ASs, but it ultimately routes based on IP addresses. Right, so instead of saying like, here's the route from AS1 to AS2, right? It routes between machines because ultimately the traffic needs to get to a machine. There are a lot of other reasons, but like that is the basic way. So you can imagine, like, if BGP is trying to, you know, talk about here are the routes sort of in and out of MIT's autonomous system, it'll be a huge pain if the advertisements have to include, like, you know, like a million random IP addresses. This is going to be a really big advertisement, a really big routing table. It's just going to get out of control, right? But we assign addresses on the internet in a special way, right? We assign them in contiguous blocks. We talked a little bit about this last Wednesday. We're not going to go into the details in this class, so you don't need to worry about the details. In particular, you don't need to worry about the details of that notation. But just know that in most cases, rather than having to deal with, say, you know, a bunch of random IP addresses, I'm dealing with a range of IP addresses, and there is a way to specify that range succinctly. Right, so that helps keep these advertisements smaller. It helps keeps routing tables smaller. All of these things, right? So all of these help with scale, right? These are all part of BGP. Although, you know, like, some things are a little bit orthogonal to BGP. They're certainly all used in this process. So now that we have scale, the next thing that we want to deal with is policy. All right. So on the internet, autonomous systems, they want a means to create routing policies, right? Maybe they want to avoid sending traffic on behalf of certain people. And so what BGP is gonna have to try to do is, in some ways, balance this desire for policy, but also foster cooperation, right? There are a lot of competitors in this space, right? Like Comcast and Verizon are competing for the same customers. So we have to think about what is incentivizing these ISPs typically to cooperate in this environment. All right. So what is interesting for us to think about today? I just like this. I like this protocol so much because it gets so messy because it involves money and how money works in the world, right? The complexity of BGP really has nothing to do with networks. All right. So the most common policy, the one we will spend the most time thinking about today, is that an autonomous system, an ISP typically, doesn't want to send traffic on a path unless it has financial incentive to do so. All right. So how does an AS know what routes are going to make money? So this boils down to understanding the typical relationships between autonomous systems. There are lots of different relationships that you might have. We're going to focus on two. They're the two most common. They're the two that you need to worry about for this class. All right. And again, these relationships come about because of how the economy works, how money works, right? Not really how networking works, right? So first relationship that we're going to look at is a customer-provider relationship, which we'll sometimes also call a transit relationship. So here we have one AS who is a customer, which is paying for access or transit, which the provider provides. So for instance, MIT buys internet access from an ISP. Like we buy internet from Comcast. We're a customer, they're a provider, right? So I'm going to keep these relationships over here on the right. On the left side, we're going to build up a more complex example. Not nearly as complex as the entire internet, but we're gonna start looking at this. So here we have one customer and one provider. Arrows indicate money. That is why I have put this helpful money emoji here on the slide for you. There's going to be so many of those emojis, right? So my provider here, the blue node in the middle, is going to make money whenever any traffic flows on this link. All right, so if the pink node sends traffic to blue and beyond, or if other ASs, which will appear eventually, if they send traffic through blue to pink, right? So arrow indicates money, traffic can flow in both directions, right? So providers themselves can be customers, and in fact, in most cases are, right? Typically, you will have, a smallish AS will buy internet from some other AS. They will be buying internet access from someone else, right? So in this diagram, my blue node in the middle makes money whenever any traffic flows on the bottom link. Purple node makes money whenever traffic flows on the top link, which brings up an interesting question, right? What happens, what happens if traffic goes here? All right, so my pink customer all the way at the bottom sends traffic to some node in the purple AS, goes all the way up. Who's making money here? All right, because it looks, like, okay, blue's gonna make money, but then it's gonna pay money to purple. It's hard to imagine. The way this works in practice, typically a provider is charging more money to its customers than it gets charged by its own provider. All right, so what that means is that typically the blue provider will charge more money to pink here than the purple provider is charging blue. All right, so in some ways, the further down you are in this graph, typically the more money you end up paying, like per byte. And I hate to tell you, but we, like, as individuals, we're at the bottom. We're at the bottom of this graph. Right, so that is how that's a typical setup. And again, this isn't a thing that is like set by BGP. This is how we pay for internet, right? So this is one common AS relationship, having a customer and a provider. So let's make this example a little bit more interesting. All right, we're going to add some nodes here on the left. All right, so, and you can see everybody's kind of, we go up to this purple node. So in this graph, we can imagine, suppose our two bottommost customers, this orange and pink node. Who's the provider of all providers? Great question. We're going to come to that. Imagine that I've got a customer inside of this AS. Wow, yellow was a terrible choice for that. Blue. All right, I've got a customer inside this AS, and a customer inside this AS, and they're talking to each other a lot. All right, so traffic is going this way a lot. Right, and so, my blue node here, my lavender node over here, they're making some money on this. They're charging orange and pink a lot of money, more money than they're paying purple. But, they're not like making as much money as maybe they could, right? So this gets us to the second relationship, all right? Peers, right? So an autonomous system can have peers, which effectively allow free access to each other's customers. So if I have my lavender and my blue node here, peer, and we'll talk about exactly how this starts to happen. Oh, geez. They're going to allow traffic to flow this way, right? Which means they are both going to make money on these links, and that peering link in the middle, it's free. All right, they don't pay each other for that transit because they're friends, they're peers. All right, now there are agreements about how this works. Typically, you want the amount of traffic in each direction to be pretty similar. These peering agreements are like they're secrets, they're business secrets. So I don't know the details of any of them. I think a feeling would be that, like, as long as the amount of traffic in each direction is sort of within like 4 times of the other direction. I don't know, Karen, does that feel right? Yeah, feel small integer number. All right, so it doesn't have to be exactly equal. That would be a huge pain to deal with, but there is an agreement here. right? So why have peers? You'd have peers for situations like this, right? If it's a mutually beneficial arrangement, right, between these two ASs, which is interesting because these two ASs here might, oh, no, might be competitors, right? Lavender and blue here, it might be things like Comcast and Verizon, right? Yet they're sort of joining forces here. They're going to make more money. And also, I don't want to make it sound like this is a terrible capitalist hellscape. It should provide better performance for the customers. This is a shorter path in many cases, right? Your traffic might get there faster. That would be great, right? There are also some topologies where peering will give us the only way to provide connectivity. We'll talk about that at the end of lecture, right? So these are two common relationships. And again, there are others. You can get really into BGP. I could probably do conservatively like 6 lectures on BGP. I love it so much. There's so much to talk about. We're just going to worry about these two, right? So how does this relationship, how does this sort of economic relationship, how is it reflected in the protocol, right? How does this expand into like actual decisions about routes? All right, so let's find out. So we're gonna start to make a slightly more complicated graph here. And so one question that I'm gonna ask you to think about. So I've made a little bit more of a complicated graph. And I'm gonna imagine a similar situation where I have, oh boy, I have a customer down here, and I'm gonna put a customer over here. All right, and so let's think, suppose we allowed traffic to flow across this set of links. So it's going to go from orange to lavender to blue to green to yellow, and potentially back and forth. All right. So a question for you is, who is this good for? Right? Who's making money here? Right? Certainly, my lavender node over here on the right is making some money. All right. That's great. Its customer is sending traffic through it. That's exactly what it wants. All right. Same thing over here. Green node is making money. Traffic is going between yellow and someone else. This is great. So let's think about that blue node, right? What's going on there, right? It's sending traffic basically from one peering link to another, right? In theory, it's not paying any money, right? But it's also not going to make money if it allows traffic to flow in this way. This isn't really a great arrangement for blue, for our node in the middle here. In fact, blue might get worried. I might say like, oh, I'm sending all this traffic, maybe in one direction through my peering links. That could try to upset, kind of upset my peering agreement with these two nodes. I don't know. Right. So in fact, blue doesn't want this to happen. Right. Blue doesn't want to allow for this. Right. So how is this going to happen? You can imagine this blue AS, maybe it tries to like block traffic on a path. That's very expensive to do. In terms of like processing on a switch, it's computationally expensive. It also might actually be what we want to do. Like maybe blue only wants to block traffic on a path if there's a better path available or something like that. So the way we're gonna see this play out in BGP, ASs will selectively advertise. Right? They will have sort of different rules about what routes they advertise and to whom. Right? These rules are known as export policies. All right. So we're going to look at typical export policies in BGP. All right. So to be clear, routes like physical links may exist, but they will not necessarily be advertised to all parties involved here. And one of the things we're gonna start to worry about, and I think some of you are anticipating this in the chat right now, with what I show you, there are going to be some places that are unreachable. So we're going to have to talk about how the internet deals with that, and it does. All right. So export policies. Let's focus in on our middle ASs. All right. We're going to come back to the nodes that I just grayed out, but let's just start here. All right. So a first common export policy is what providers do. So providers have an incentive to get as much traffic to and from their customers as they can. So this blue node in the middle wants everyone in the world to know about its customer, right? Because it would love for everyone in the world to send traffic through it to its customer. Similarly, it wants its customer to know about everyone else because it would love the customer to send traffic through it to everyone else. All right, so in terms of the routes it exports, blue is going to tell its provider, like, hey, I have this customer, I can reach them. Right, and it's going to tell its customer about this purple node. Hey, I have this, right? Because there may in fact be like machines in here that our pink customer wants to send to. All right, and so this is this is probably what you expected. This is kind of what we would expect to see in a network. Blue can reach these two different nodes. It wants to let them know about it, right? And again, the incentive here is get as much traffic to your customer as you possibly can. Right, so now what happens when we have peers, right? Because peering is a little bit different, right? So let's add back in our peering, and right now we're really just focused on what the blue node does. All right, who is it telling about whom? Okay, so let's think this through. Blue node's got routes to its pink customer, it's got routes to its purple provider. It's going to say something to its peer, to this green node. All right, so okay, does it have incentive to tell the green node about its customer? Sure, it does. It would love traffic to go, say, through here, right? Or maybe eventually through here. It's going to make money on that. That would be great. But does it want the green node to know about its provider, right? Would it want to allow traffic to do something like this? Or maybe even this eventually? Not really, right? Blue is going to lose money on this deal, right? Because it's going to have to pay money to send data on this part, right? It doesn't want this to happen. And the way that it's going to do that is by selectively advertising, right? So with peers, we're just going to tell each other about their customers, right? So blue node is not going to tell the green node about the purple node, right? They're not going to tell each other about their own providers. We would lose money, right? And again, this might start to get concerning, right? And it should be concerning, right? Because let's think, I sort of just illustrated here like we could maybe call it a round of advertisements for BGP. We don't always, that's the word I use on the slide. I realize we don't always speak about rounds in BGP, but I think it makes sense here. Right, so once we think a little bit more about this graph, right? Certainly the blue node, it does want to tell its customer about other places it can reach. Again, it wants that customer to be sending as much traffic as possible. All right, so after all of this happens, all right, you can examine. I focused on these two customers down here. So our pink node's going to end up knowing about routes to everywhere else. But that yellow node is not going to know about a route to the purple provider. It doesn't know how to get there. Nobody tells it, right? And in fact, if we get back to our slightly more complex example, there's quite a few nodes here that have no way to get to the purple node, right? So BGP itself provides no mechanism to prevent this, which might seem strange. In fact, the first time that I encountered an example like this, I thought, well, this has got to be the worst routing protocol, because in some ways it's doing one of the worst things that a routing protocol could do. There is a path, right? There is so clearly a set of links that could get us from any node to any other node here. And yet various autonomous systems aren't learning about that, right? And what do we do? Okay, well, in the real world, this is not what the internet looks like, okay? In the real world, we have some other things going on, all right? So typically, almost everyone buys internet from someone else, all right? So these two autonomous systems on the edges here, they would have their own providers. This in and of itself doesn't help us, but we're getting towards the internet. And in fact, we actually have another layer. I kind of ran out of colors here. So we typically have a structure like this, right? Where we have sort of just things that are only customers down here at the bottom. And then we have sort of tier 3 ISPs, tier 2 ISPs, and tier 1 ISPs. And the thing that is special about the tier 1 ISPs is that they are all peers with each other. All right, this is still a remarkably simplified diagram of the internet. You would expect to see a lot of other different types of relationships. There can be more peering links around here. There are a ton more ASs. But let's think about why this helps us. All right, what does this allow for? So say we have a customer over here in our orange AS. I don't really need the tiers anymore. All right, so a customer here in the orange AS. That, the green on orange is a real look. We're gonna do red. All right, so a customer here, and it wants to, it wants to send data to a customer or a machine inside of that purple node, which couldn't be done before. All right, now, in fact, we can have traffic going like this. So you can double check with the export policies that I provided to you, this route will be available. All right, so that's one example. Another example that I'll give to you, let's see, suppose we wanted to send data sort of all the way, like from orange to yellow, right? That can happen through something like this. All right, you might look at this and say like, oh, that feels like it's gonna take a long time. Like, yeah, potentially. That's why you might expect to see other sorts of peering agreements, right? Remember that at the very beginning, we talked about, say, this set of peers. That's in theory going to be much better performance than doing something like taking traffic all the way up here. Right, so there are a lot of reasons to peer, and again, you'd expect to see lots of different peering relationships in here. Right, but all of the tier 1 ISPs peer with each other. That is what makes you a tier 1 ISP. And there are not too many of them. There are 10, 15-ish, right? These are really, really massive tier 1 ISPs. So this is how the internet enables you to have connectivity to anywhere through BGP. Can peers form between different levels of providers? Yeah, I don't know how common that is. I'll let someone else on the staff jump in if there are like, if you would expect to see peers, say, between like a tier 3 ISP and a tier 2 ISP. I will say those definitions themselves are pretty loose. All right, like there's no like hardcore definition of what it means to be tier 3 and what it means to be tier 2. So yeah, you totally could see that, but I would expect that it's a little bit less common. But I'll let the staff jump in and correct me if I'm totally wrong. All right, so this is a simplified version of the internet. It's a lot of colored circles. All right, we've talked about export policies. This is not actually all of routing though. This is about who sends advertisements to whom. Once you start getting those advertisements, what do you do with them? Right? Like imagine you're all autonomous systems. You start hearing about lots of different paths to lots of different places. And you're going to probably hear like about multiple routes to a particular AS. Right? So how do you decide? Right? Another way to say that is, what are your import policies? What routes are you going to import? All right? Which routes do you actually use? An exciting thing about BGP, ASs get to decide, right? Typically, if an AS is hearing about multiple routes to a destination, it's going to prefer to use its customers first, and then its peers, and then its providers, for the same financial reasons that we discussed with the export policies. But sometimes that might not be enough, right? You might hear about a route to a destination through 2 different peers, right? How do you choose between them? BGP provides you with a variety of other attributes to use this. So you might break a tie based on hop counts. That's a common one, to just prefer fewer hops through the network, right? But the real important thing, which I'll come back to, is that ASs get to set their own import policies. They get to make these decisions themselves. All right, so to tie this back to routing, before we talk a little bit more about sort of how BGP is doing today, we can think about BGP as a distributed routing protocol, just in the same way we did with link state and with distance vector. right? So in those routing protocols, we start with some sort of hello protocol. BGP has a version of this, right? In BGP, we talk about ASs sending keep alive messages to neighbors. It serves the same purposes, right? If there's a failure, you'll be able to discover it through those messages stopping or getting disconnected or something like that, all right? Advertisements, what do advertisements look like? Oh boy, they contain so much interesting stuff, right? They contain lots of information, right? And they look different depending on, you know, whom they're being sent to, right? We've covered that. That's part of the export policies, right? Route integration happens via these import policies, right? So ASs integrate routes based on their set policies. One interesting thing to deal with failures in BGP, you can explicitly withdraw a route, right? So you can say this route is no longer valid. Like you can send an explicit message saying that this route no longer exists, right? So one other thing to make note of here is sort of where does BGP live, right? Where does it live in this layered model, right? I didn't highlight it at the network layer for you. It is actually an application layer protocol, even though it deals with routing, right? So this is also a great place to make a distinction. Again, we covered this on Monday, but a distinction between the processes of routing versus forwarding, right? Routing is the process of building up routing tables. Forwarding is an action that a switch takes on every single packet, right? It looks up a packet, figures out where it's destined to go, and then sends it out on that link. So you're going to talk a lot more about BGP in relation to layering in recitation for the next 2 recitations, in fact. But one of the things that is sort of interesting about BGP is a routing protocol. It sits at this application layer, sits above things like transport. BGP actually runs over a reliable transport protocol, right? So that means we do not worry so much about advertisements, BGP advertisements getting lost. They can, right? Even the best reliable transport protocol cannot guarantee things 100%. They are still best effort. But that is an interesting thing about BGP and about dealing with failures, right? So even though it deals with routing, it actually lives more at this application layer. All right, so again, I also want to reiterate Mark's comment in the chat. This is a vastly simplified diagram of the internet. In fact, we'll come back to it again. If you remember the picture that I've been putting to you, I've been showing you at the beginning of lectures, that sort of blue ball, that is the AS graph, all right? So it's much messier. It's not as layered. It's not even necessarily planar as Mark mentioned. But you know, in my world, on my slides, it's beautiful and colorful. Okay, so let's think. Does BGP scale? That's what we set out to do here, right? Well, okay, it works on the internet. So to some extent, yes, it's done quite well. But there are a few things now that are starting to limit the scale of BGP. I'm gonna run through 4 of them. So one is simply the size of the routing tables. We try to keep BGP routing tables small, try to succinctly express prefixes, aggregate routes when we can. There are a lot of tricks there. But even still, a full BGP table is pretty big. It can exceed the amount of memory dedicated for the table in many routers. So we're getting a lot of ASs on the internet, a lot of machines on the internet. That's pushing the scale. Second thing, so routing table size. Second thing, route instability. BGP is managed by humans. We frequently see misconfigurations, right? You saw an example at the beginning when we talked about the Cloudflare outage that was caused by a misconfiguration. Another thing that misconfigurations can cause is, like, a common manifestation of that is a router is sort of frequently going between like up and down states, right? And so what we see is a BGP router might announce that a route exists and then withdraws the route, right? Explicitly withdraws it, and then announces it and withdraws it and announces it and withdraws it, and just keeps doing this over and over and over, right? You can even see these types of oscillations when there are no misconfigurations. They can result just from the fact that autonomous systems choose their import policies are their own policies, and sometimes they conflict, right? So there's a mechanism built into BGP to prevent this type of oscillation, or basically to ignore it, right? So BGP routers can just ignore advertisements that oscillate in that way, that change. The mechanism is known as route flap damping. That technique, it can improve scale. It helps us sort of ignore those routes and sort of converge eventually, but it does increase the time it takes to learn about new routes and to install new routes and things like that. All right, so routing table size, route instability. Third thing, multi-homing. All right, so I told you that there are a couple of other different types of relationships between ASs. So we've only talked about two here, but another one, it is totally allowed for an AS to buy internet from multiple providers. So something like that. This is a multi-homed ISP. There are a couple of reasons you might want to do this. Good reasons. Some customers might buy, they're buying transit from two ISPs, the idea being that one is going to be a backup. All right, so we're going to buy internet from Comcast, and if Comcast goes down, we'll switch over to our Verizon backup, right? Something like that. I believe that MIT is a multi-homed AS. I don't know if we do it for that reason or not. Another reason you might try to do this is to load balance, right? To say in some way like, okay, I'm going to send half my traffic through Comcast and the other half through Verizon, right? To kind of balance those links, right? Not bad reasons. Those are not bad reasons to do this. But as the number of multi-home networks grows, so does the routing table. Doing that load balancing tends to be tough and can lead to unintended consequences. Essentially, you're adding complexity into a graph that is already pretty complicated, right? So that is preventing scale. And then one of the last things that we're going to talk about is IBGP. So the I is for internal. IBGP just refers to the protocol that runs within an AS. All right, so imagine we got our little AS over here, and you can have a couple of gateway routers. So again, these are the routers that are speaking, typically link state on the inside and BGP on the outside. All right, but they themselves need to be consistent in some ways, right? They're all operating for the same AS. They want to be advertising the same things, importing the same things. IBGP is the protocol that helps us deal with that. The way that IBGP works requires these gateways to be completely connected. All right, they are a completely connected graph. They all are directly connected to one another. This itself, when it's 4 gateway routers, you get this beautiful little picture. It's not a big deal. If the size of your AS grows, the number of gateways probably needs to grow. This network, to remain complete, it gets hard to manage, right? It can be hard to scale BGP within an AS, right? And again, we're not going to worry about the details on IBGP at all, but it's important to know that it matters here when we think about the scalability of BGP, right? And the internet has grown so large, scalability is starting to be quite a concern here, right? Now, we haven't gotten to this part of O33 yet, but this is a great time to start asking ourselves questions like this. Is BGP secure? It is not. It is super not on its own. Okay, so what does that mean in this context? There is nothing about BGP that makes sure the routes that are being advertised are true. Okay, I do not normally look on Twitter for lecture content. I do not normally look on Twitter for anything, but I do enjoy this tweet very much, right? BGP basically relies on the honor system, right? So BGP was not designed with security in mind. We will talk more about this later on in the class. You can do, boy, can you do all sorts of things. If you do some Googling around for BGP hijacking, that's a thing that can be done. But really, there's nothing preventing me from showing up, like starting my own AS. Okay, we'll move on. So here's me. That's Katrina, the Katrina AS, showing up and saying, hey, I can reach everybody and my routes are really short. You send all your traffic to me, right? Now, eventually people would potentially realize that if I just took their traffic and dropped it, right? But there's nothing in BGP that stops that from happening. There are proposals for securing systems like BGP, right? Similar to how there are proposals for systems to secure DNS. We will talk about at least one of them in a lot of detail as we go on the rest of 033. But they're hard to deploy globally, right? You kind of got to get everybody on board, right? And we're talking about a global system of ASs, right? Those types of systems can also be really slow. They can slow down the processes here. All right, so BGP does scale, but it, starting to run into issues, and BGP is not secure. All right, so where does this leave us? All right, and so again, I should have called this out at the beginning. This picture that I've been showing to you, if you paid close attention to the caption, is the AS core as of 2017. So these dots, they're not individual machines, they're autonomous systems, right? And you can see now why this is not the example that I used in lecture. Imagine trying to do that. But this is the statement that I gave you at the end of the first lecture. To me, the reason why I think BGP is the most interesting protocol, it is to me the best example of what makes the internet different from a lot of other networks. Here is a place we have to deal with just the massive scale, the biggest network we have, right? Massive scale. We have to support a diverse group of interests, competition, right? Economic competition. We somehow have to foster global connectivity, even among different ISPs that might be competing with each other. So I think that BGP, it gets messy because it involves humans and it involves money, right? And that is why it is my favorite protocol. Also, I just generally like routing. So that is it for BGP. We have an extra 3 minutes. You can go out and enjoy the day, or we will answer some questions for you. As you can see from the chat, the staff is also big into BGP. So let me stop sharing and I'll stop recording.